Hello and welcome to Lecture 7 of our course on stochastic modeling of biological processes. In Lectures 4, 5 and 6, we illustrated that stochastic modeling can be useful for systems with multiple stable steady states of deterministic ODEs, for systems close to the bifurcation points of deterministic ODEs, and for systems with low molecular numbers of at least one chemical species. In each case, we started with a given chemical reaction system and we were interested to study its properties, whether its solution converges to a steady state, whether it oscillates, and how it depends on the system parameters. To do that, we wrote the corresponding deterministic model as a system of ordinary differential equations and we analyzed it. Then we implemented the Gillespie stochastic simulation algorithm and highlighted the differences between the deterministic and stochastic modeling. In some cases, we could also further analyze the stochastic model using the corresponding chemical master equation. However, we can also invert our approach and ask a different set of questions about designing chemical reaction systems with prescribed properties. That is, we can start with a set of properties that a target chemical reaction network must have and aim to construct a chemical reaction network satisfying this set of properties. Engineering chemical reaction networks is the aim of a relatively new interdisciplinary scientific field called synthetic biology. It can be done by altering a pre-existing intracellular network, but one can also engineer a network from scratch. For example, in DNA computing, reaction networks are engineered with chemical species consisting exclusively of DNA molecules and can be used to physically represent a very rich set of theoretically designed chemical reaction networks. Depending on our input, there might be multiple possible outputs. There might be several different solutions, and it is sometimes difficult to say which one is the best one. The resulting output chemical reaction networks can have very different properties. However, as long as they satisfy the properties which we want, we are happy with such outputs. So let me start with an example. Let us consider that the property which the reaction network should have are oscillations. We would like a system which has periodic solutions, as I have shown in this plot. We would like a system with a stable limit cycle. So starting with an initial condition, we would like solutions to converge to this limit cycle. So our questions are, can you design a chemical system which oscillates? Can you design a chemical system such that its deterministic ODE description has one limit cycle? Now I will give you 5 seconds to think about these questions. But if you need more time, you can press the pause button. There are many different answers to these questions. One possible output is system 2.9, which we studied in section 2.2. We showed that this system has a stable limit cycle for some parameter values, so it can be used as a possible answer to our questions. There are many other answers, and your answer could be different than mine. Moreover, we have seen some plots of the time evolution of this system in section 2.2. They do not look exactly as I plotted here. But this is not an issue, because I did not want to quantitatively fit this illustrative drawing. I'm not trying to fit here any experimental data, but my aim has been to design a chemical reaction network which has desired qualitative properties. This was very easy, so let us make our problem more interesting. My next example is to construct a chemical reaction system which has two limit cycles. I have schematically drawn the time evolution of such a behavior here. Depending on the initial condition, the solution of deterministic ODEs will converge to one of the two limit cycles. The blue trajectory converges to the first one, and the green trajectory converges to the second limit cycle. So my updated question is, can you design a chemical system such that its deterministic ODE description has two stable limit cycles? It could take you more time to find an answer to this question. We do not have such an example in the lecture notes. If you succeed, It is possible to make this task even more complicated by requiring to design a chemical system with just 3 limit cycles, 4 limit cycles, and so on. More exotic behavior will require more thoughts, and it is also more difficult to observe such exotic dynamical behavior in simple systems. For example, if we restrict our considerations to systems of two chemical species, A and B, then the deterministic ODEs are plain autonomous systems with polynomial right-hand sides. In the year 1900, David Hilbert presented a list of problems in mathematics at the Paris conference of the International Congress of Mathematicians. They are very famous mathematical problems, more than 100 years old, and the second part of Hilbert's 16th problem is about the number of limit cycles in such systems. It is unresolved to date, but example systems with multiple limit cycles have been constructed. If we consider chemical reaction systems which only have zeroth order, first order, and second order reactions, then the right hand side is a polynomial of degree 2. For such ODEs, nobody has yet found an ODE system with 5 limit cycles. Moreover, not every polynomial right-hand side corresponds to a chemical system. And for chemical systems, we also want all concentrations to be non-negative. So we have further restrictions on positions of the limit cycles. We also want them to be stable. However, let us assume that you can find such a chemical system and let us think about its stochastic modeling. Having two stable limit cycles is analogical to having two favorable states. So stochastic modeling can be further used to pose additional questions. Can we design a chemical system which can switch between the limit cycles? I have schematically illustrated such a behavior here. The stochastic system oscillates around one of the limit cycles with some fluctuations. Then the noise is occasionally large enough to switch to the second limit cycle, and we stochastically switch back and forth. In a similar way, as systems with multiple favorable states can stochastically switch between them. If we have a chemical system, then we can use the Gillespie algorithm to simulate its behavior to check what is the role of stochastic fluctuations on the system dynamics. Unfortunately, some theoretical systems with multiple limit cycles in the literature can have limit cycles of very different magnitudes. If I plotted them in one plot, as I schematically illustrated here, then I would not see one of the limit cycles because it is much smaller than the other one. Even if the deterministic ODEs have limit cycles of comparable size, then the Gillespie algorithm might not lead to this behavior. If stochastic fluctuations are larger than limit cycles, then we would not see them. And if the stochastic fluctuations are too small, then we would never switch between the two limit cycles. Fortunately, one system of deterministic ODEs can correspond to infinitely many different chemical systems, which have different stochastic dynamics. In particular, there is some way to adjust the amount of stochastic fluctuations, which we add to the deterministic ODE model by considering the corresponding stochastic model. So for the rest of this lecture, I will focus on illustrating this red point. I will not design a chemical system with the stochastic dynamics sketched in this picture. I think it is difficult and my plot is just a sketch, what I would like to observe, but it does not come from a simulation of a real chemical system. However, if you find this course too easy, please try to find such a system, and if you succeed, please do send me a chemical reaction system with such an interesting dynamics. I would be very interested to see your answers. Having motivated our discussion, let us now illustrate that it is possible to dramatically alter stochastic behavior of a chemical system without changing its deterministic ODEs. In section 2.4, we revisit the degradation production system, which we discuss in detail in section 1.2, where we showed that the number of molecules of A fluctuates around the steady state of the corresponding deterministic ODE model. Next, we will modify this chemical system into another system which has the same deterministic description But its stochastic model will be very different. It will switch between two favorable states. Both reactions in the degradation production system include this symbol, empty set, which denotes chemical species which are of no further interest. However, we can obtain similar dynamics of A if we explicitly consider other chemical species. For example, consider a system of three chemical species A, B, and C in a container of volume nu, which are subject to the following four chemical reactions. The first reaction is the degradation of A, but instead of using the empty set symbol, we denote the product by B. The second reaction is the production of A, but instead of the production with a fixed rate, we assume that chemical A is produced from chemical B with the help of chemical C, which is itself produced in the third reaction, and catalytically degraded with the help of chemical B in the last reaction. Looking at this system, we observe that A and B satisfy the conservation relation that A plus B is constant. Indeed, the first reaction produces B and removes A, so it does not change the sum A plus B. The other reactions do not change the sum either. Therefore, our initial condition will determine what this constant is. In particular, the number of molecules of A must always be less or equal to this constant. Therefore, these two systems cannot have exactly the same dynamics because A has been Poisson distributed in my original degradation production system. And so A can take arbitrarily large values with a very small probability. In my simulations, I will choose this constant to be 20. So A plus B is 20. Then the comparison of both models is shown here. In both cases, I plot the corresponding deterministic solution as the dashed line, together with 5 realizations of the Gillespie algorithm. The left panel is in the lecture notes as figure 1-2a, and we have already seen it multiple times in our lectures, including the step-by-step instructions how to produce it in MATLAB in our lecture 2. The right panel is for the extended model with three chemical species A, B, and C. We chose our conservation relation to be A plus B is equal 20. In particular, A can only take values up to 20 in the right panel. However, it does not make much difference because A has a very small probability to reach 20 in the left panel anyway. In summary, I hope that this picture can persuade you that both models have approximately the same dynamics. So let us look in more detail into our new version of the degradation production system. It is written in terms of three chemical species A, B, and C. Its deterministic ODE description is given as a system of three ordinary differential equations for concentrations of these three chemical species. Again, I have denoted the corresponding concentrations by lowercase letters a, b, and c. However, one polynomial ODE system can be the deterministic model of many different reaction networks. For example, let us add two more reactions to our chemical system. They are given here. They have the same value of the rate constant, K5. Since A is produced in the first reaction, it corresponds to the term K5AB in the first differential equation. However, A is also removed by the second reaction with the same rate constant K5. So there should be minus K5AB in the first differential equation as well. In particular, the terms corresponding to the first reaction will cancel with the terms corresponding to the second reaction. So K5 will not appear in the deterministic ODEs at all. However, the stochastic model will be different for each value of K5. Therefore, we can add noise to different parts of the state space by adding suitable reactions of this form. without changing the deterministic ODE dynamics. In Figure 210 on page 53, we present the time evolution of both deterministic and stochastic models for two different values of rate constant k5. Since the deterministic ODE model does not depend on k5, it is the same result in both panels, visualized as the dashed line. The left panel is calculated for k5 equal to 0. This means that the last two reactions are not included at all, and our model simplifies to the degradation production chemical system. The right panel is for a larger value of K5. It shows switching between two favorable states of the system, one around 0 and the other one around 20. These states have nothing to do with the ODE, which is the same in both panels, and gives its steady state to be around 10. While this result could look counterintuitive to some of you, it is actually what we could expect from our model for larger values of K5. If K5 is large, then these two reactions will happen very quickly, provided that there are some pairs of reactants available in the system. Since the sum A plus B is equal to 20, there will only be two states when this reaction cannot happen. Either A is equal to 0 and B is equal to 20, or A is equal to 20 and B is equal to 0. Otherwise, these two reactions can occur. If we increase the value of K5, then the system dynamics will quickly leave any state of the system except the state when A is equal to 0 or 20. Figure 211 on page 54 shows the dependence of the stationary distribution on the parameter K5. It has one favorable state around 10 for K5 is equal to 0, and it changes to two favorable states as K5 is increased. The right panel shows the stationary distribution for a different chemical system, where we added the following two reactions to our degradation production system. They again have the same rate constant, denoted K6, and they have again been chosen in such a way that the deterministic ODEs do not depend on K6. In this reaction, 10 molecules of A react with 10 molecules of B. Since the sum A plus B is equal to 20, this reaction can only happen if there are exactly 10 molecules of A and 10 molecules of B in the system. If we make the rate constant K6 very large, then this reaction will happen very quickly whenever there are exactly 10 molecules of A and 10 molecules of B in the system. So the system will not spend much time in the state when there are 10 molecules of A in the system. This is clearly visible in the plotted stationary distribution for larger values of the parameter K6. This also shows that we can add extra noise, extra stochastic fluctuations to very specific parts of the faceplane. This brings me to the end of lecture 7, where we concluded with our discussion of chapter 2, covering section 2.4 on designing stochastic chemical systems with prescribed properties. We showed that one polynomial ODE system can be the deterministic model of many different chemical reaction systems. Stochastic models of some of these chemical systems can have very different behavior. Please read section 2.4 on pages 49 to 55 of the lecture notes before watching the video of lecture 8. Thank you for listening to lecture 7 of Oxford course on stochastic modeling of biological processes. Bye bye.